Welcome to the Deep Dive. This is where we take your pile of information, maybe articles, research, could even be your own notes, and we pull out the most important nuggets of knowledge, the insights. Our whole mission here is to give you a shortcut, basically, to being truly well-informed, complete with those aha moments, those surprising facts that really make learning stick. And today, we're diving into something pretty specific, tailored just for you. We're going deep into React.js, specifically exploring what it really takes to go beyond just, using the library to actually building up an architectural mindset. Our guide for this is a really insightful report called the React.js Architect's Blueprint.
Yeah, and what's fascinating about this blueprint is how it lays out the whole landscape, all the skills you need to build robust end-to-end products using React. It's less about the specific lines of code, what to type, and much more about understanding why. Why choose certain patterns, certain tools, and what are the long-term implications for performance, scalability, maintainability, all that stuff.
That's such a crucial distinction. So if you've ever felt maybe a bit overwhelmed by just the sheer volume of stuff in the React world, or if you've wondered, what really separates a good developer from a great architect, well, then this deep dive is definitely for you. We're going to unpack the foundations, the prerequisites, and the core mental models React asks you to adopt, how to craft those interactive UIs, and then really elevate our perspective. Think like a true architect, making those critical decisions about application structure, performance, the whole professional lifecycle. Okay, let's get started. So our journey kicks off with what this blueprint calls the foundation mastering the prerequisites. And it really stresses this point, trying to learn React without deeply understanding the tech underneath it. It's like trying to write a novel without mastering grammar. You just can't build something solid.
Yeah, it raises a really important question. What exactly are these foundational building blocks? Because so many people rush straight to React, right? But if you only have a superficial grasp here, it just inevitably leads to flawed architectural decisions later on. Guaranteed.
First up, HTML and CSS. Sounds basic, maybe. But React doesn't replace them. It builds right on top of them. The blueprint makes it clear. A weak foundation here. That leads to poorly structured apps, inaccessible ones, inconsistent ones. Just a mess, really.
Right. And when we talk HTML, for an architect, the emphasis has got to be on semantic HTML, using tags like header, footer, article, AP for their actual meaning, not just as hooks for styling. And this isn't just, a stylistic preference. It's absolutely critical for web accessibility, A11Y as people call it, for screen readers. And it directly impacts SEO. Search engine crawlers rely on that semantic meaning. An architect gets that HTML tag choices have real, tangible business implications.
Yeah, that's a great point. And then there's advanced CSS. It's way more than just colors and fonts when you're building something serious. You need a deep grasp of the box model, how content, padding, border, margin, how they all interact. Specifically, understanding content box versus border box. And importantly, using a CSS reset to enforce border box globally. That gives you predictable layouts, which are so much easier to reason about in a big app.
Absolutely. And from that bigger picture perspective, mastering modern layout systems, things like Flexbox and Grid, plus responsive design using media queries, maybe a mobile-first approach. These are just baseline expectations now for creating fluid UIs in production. Without that foundation, your UI just won't hold up. Not with all the different devices and users out there.
Okay, now JavaScript. This is where the blueprint says things get really interesting. It calls rushing through JavaScript to get to React the single most common mistake. It emphasizes, and I think this is key, React is, at its core, just JavaScript. People sometimes forget that.
It's so true. If you're interviewing for a React role, they almost always test your JavaScript fundamentals first. Because honestly, that's a much more reliable indicator of a developer's potential than just knowing a specific library's API, right?
Yeah.
Take this keyword, for example. In the older class-based React components, understanding how this worked in JavaScript was critical because event handlers would lose their context, this value, and you'd be forced into manually binding them all the time. It was a pain.
Right. And the beauty there is how modern JavaScript, specifically ES6 arrow functions, gave us such an elegant solution.
Yeah.
Because they lexically inherit this context. They don't have their own. So knowing that why in JavaScript makes the what in React feel, well, almost obvious. It just clicks.
Exactly. And production level React absolutely leans heavily on modern JavaScript features. We're talking let and const for block scoping. And the advice is usually prefer const by default, only use let, if you actually need to reassign the variable, and arrow functions, of course, not just because they're concise, but crucially because they avoid having their own, this binding really simplifies context management.
Yeah, you see them everywhere. And destructuring, too. You'll see that all over React code. Accessing props, working with hooks, like with useState. You're constantly writing const count, set count, useState, use0. It just makes the code so much cleaner, so much more readable.
Definitely. And the spread and rest operators, they look similar, same syntax, but they do very different things. The spread operator, specifically, is fundamental for React's whole immutability principle. You use it to create new arrays or objects with updated values rather than changing the original ones, and that's absolutely vital for predictable state management. React relies on that.
And we can't forget ES6 modules, right? Import and export. Understanding the difference between a default export and named exports is pretty critical for structuring projects that can actually scale.
Absolutely essential. And finally, those higher order array methods, things like .map, .filter, .reduce. These are the workhorses in modern React development, especially .map for rendering lists of data into JSX elements. It's just the idiomatic way you do it now. It fits the functional style.
Okay, so modern web apps are constantly fetching data, right? Promises with .then, .catch. They definitely gave us a cleaner way to handle that async logic. Helped us avoid that nightmare of callback hell, those deeply nested callbacks that make code almost impossible to read, let alone debug.
Oh yeah, callback hell was rough. But the modern standard now, and for very good reason, is async await. It's really just syntactic sugar built on top of promises, but it lets you write asynchronous code that reads almost like synchronous code. And it greatly simplifies error handling, too, using standard try.catch blocks. It just makes complex data flows much more approachable, much easier to reason about.
And beyond the code itself, there's the whole tooling ecosystem.
Yeah.
Node.js and NPM, or maybe Yarn. They power everything. Bundling your app, managing all those dependencies, and just being comfortable with the command line interface, the CLI, that's totally non-negotiable. You need it for basic stuff like npx create React app or just npm start.
For sure. And then there's Git. Now, a beginner learns the basics, right? Git init, add, commit, push, pull, branch, merge. But an architect understands that Git's fundamental design, its distributed nature, directly enables key business outcomes and team workflows. Being distributed lets teams work in parallel, even offline. And the whole feature branch workflow, which Git makes so cheap and easy, that's the cornerstone of continuous integration in agile teams. It's built on Git.
So what does this mean practically for you, the listener? Well, platforms like GitHub, GitLab, Bitbucket, they build on top of Git with things like pull requests. And pull requests aren't just about merging code, they're formal mechanisms for code review, for discussion, for quality assurance. Put it all together, Git, branching, PRs, and you facilitate a truly agile workflow, which leads to faster, more reliable release cycles. It's a core piece of architecting for team collaboration and ultimately speed. Okay, so we've covered the must-knows before React. Now let's shift gears and talk about how React itself asks you to think. It's about internalizing its conceptual framework, moving past just the syntax to really think in React. First up, the virtual DOM, or VDOM. This one's often misunderstood. A lot of developers think it's just about making things faster than manipulating the real DOM directly. But the blueprint clarifies that's kind of a misconception. Yes, direct frequent manipulation of the real DOM is expensive, performance-wise, but the VDOM's purpose is deeper than just raw speed.
That's exactly right. The true genius, I think, of the VDOM is that it acts as an abstraction layer. An abstraction that enables React's declarative API, letting you just say what you want the UI to look like while optimizing the performance of updates. It's a fundamental shift from telling the browser how to update step by step to just describing your desired end state. React figures out the how.
And the process React uses under the hood, called reconciliation, it's actually pretty clever. So after a state change happens, React creates a new VDOM tree in memory. Then it runs a very efficient diffing algorithm to find only the minimal differences between the new tree and the old one. And finally, it patches the real DOM, applying only those necessary changes, not rebuilding everything.
Exactly. By batching those updates and only touching the specific DOM nodes that need changing, React significantly minimizes those costly performance-hitting DOM manipulations. So yeah, the VDOM isn't a replacement for the actual browser DOM. It's an intelligent optimization strategy. It's what makes that declarative developer experience performant enough for complex UIs, which brings up an interesting point, actually. How does this differ from something like the shadow DOM? People sometimes confuse them.
That's a good question. Shadow DOM, for anyone unfamiliar, is a browser technology. It's primarily used for encapsulation. Think about how a built-in video tag or maybe a complex date picker works. They have their own internal structure, styles, and scripts that don't leak out or clash with the rest of the page. That's Shadow DOM.
Exactly. So Shadow DOM provides true encapsulation, often used for web components, whereas the virtual DOM is a React-specific concept. It's internal to the library itself. Its whole purpose is managing efficient updates to the regular DOM based on state changes in your React components. So yeah, completely different purposes.
Okay, next concept, JSX, JavaScript XML. It lets you write what looks like HTML directly inside your JavaScript code. But it's not HTML. It's actually a stricter, arguably more powerful syntax. And it gets transformed into plain JavaScript during the build process.
Right, and the blueprint points out 3 fundamental rules you got to follow with JSX. 1, you must always return a single root element from a component's render, though you can use React fragment or the empty tag shorthand to avoid adding unnecessary extra nodes to the DOM. 2, all tags must be closed. Even self-closing ones like img or input dead gotta have that closing slash. And 3, you generally use camel case for HTML attributes that become props. So class becomes class name, or becomes HTML4, stroke width becomes stroke width, things like that.
And the real power, for you, the developer, comes embedding dynamic JavaScript expressions right inside your markup using curly braces. You can render variables, result of calculations, even function calls directly within the JSX. It makes dynamic UIs incredibly flexible to build.
Yeah, and understanding why JSX has these specific rules really helps demystify it. It's pure syntactic sugar, remember. Under the hood, during the build process, a tool like Babel converts all that JSX into regular React.createElement function calls. Knowing that transformation happens explains why those stricter rules exist, because ultimately it's all just JavaScript being generated.
Okay, maybe the most fundamental philosophy of React, breaking complex UIs down into small, independent, reusable pieces. We call these components.
Yes, and this directly applies a core software design principle, the single responsibility principle, or SRP. Ideally, a component should do only one thing, have one reason to change. If it starts getting too big, handling too many different concerns, well, that's a sign an architect should look to decompose it, break it down into smaller, more focused subcomponents.
So for you building an app, it means you construct complex user interfaces by composing these small, single-purpose components together. You nest them, creating a hierarchy. And this promotes reusability across your entire application. It also leads to a clean separation of concerns, which is absolutely essential for maintainability, especially when you're working in larger teams or on complex code bases.
And a major architectural shift that we've seen solidify over the last few years is the move towards functional components as the standard way to write React. With the introduction of hooks back in React 16.8, functional opponents suddenly gained the ability to manage their own state and handle side effects, things previously only possible in class components. This led to code that's generally more concise, often easier to read, and importantly, easier to test compared to the older class components. It really streamlined the whole development experience.
Okay, so once we've internalized React's principles, it's time to master the specific tools that actually bring those components to life. We're talking props, state, effects, and handling events. Let's start with props, short for properties. They're the main way React components communicate. They facilitate a strict, one-way data flow, always moving from parent components down to child components. You pass them down just like you'd pass HTML attributes. And pretty much any JavaScript value can be passed as a prop strings, numbers, booleans, arrays, objects, even functions.
Yeah, and a very standard convention you'll see everywhere is using JavaScript destructuring right in the child component's function signature. It cleanly extracts the specific properties the component needs. So think of maybe an avatar component. It might receive person object and a size number as props. Destructuring lets you pull those out directly, like function, avatar, person, size, making the component signature very clear about exactly what data it depends on.
And don't forget the special implicit prop. Props.children. This is really powerful. It lets a component act as a generic wrapper or container, like you might have a card component. Props.children lets you put anything inside that card's opening and closing tags in JSX, and the card can render that content. Super flexible for layouts.
Absolutely. Now, there's one core inviolable rule about props. It's crucial for predictability, especially in large apps. Props are read-only, immutable from the child's perspective. A component must never, under any circumstances, try to modify its own props. This principle of mutability is fundamental to how React works and how it keeps track of changes. If a component needs to somehow change a value it received as a prop, it has to essentially ask its parent to send down a new prop value. Usually this is done by calling a function that was passed down as a prop from the parent.
Right, so props are for external data coming into a component. State, on the other hand, gives a component its own internal memory. State lets a component track things, respond to user interactions, change over time. And the useState hook is your primary tool for adding state to functional components.
It's pretty straightforward. When you call useState, it returns a pair of values in an array. The first item is the current state value itself, and the second item is a function that you use to update that value. So you'll constantly see that pattern. Const count, set count, useState 0. Simple, elegant.
Okay, now here's a point that often trips up developers, especially if they're coming from frameworks with different models. State updates in React are asynchronous, and they might be batched together by React for performance reasons. What this means is, if you call, say, set count, count plus 1, twice in the same function, back to back, you might find the count only increments by 1, not 2, because both calls might have used the same count value from the initial render before either update was processed.
Exactly. It's a common source of bugs. The robust solution, the one you should almost always use when the new state depends on the previous state, is the functional update form. So instead of set count, count plus 1, you write set count, prev count plus 1. You pass a function to the setter. React guarantees that prev count will be the most up-to-date previous state value. This prevents race conditions and ensures updates happen predictably, especially with rapid or complex interactions.
Another crucial point, tying back to immutability. When you're dealing with objects or arrays stored in state, you must never mutate them directly. For instance, don't do something like user.age plus 1 and then set user. That's a fundamental React no-no. It breaks React's change detection.
Right. Instead, you must always create a new object or array, typically using the spread syntax, copy over the old values, make your changes to the copy, and then pass that completely new object or array to the state setter function. This is because React, for performance, usually does a shallow comparison of references to detect changes. If the object reference itself doesn't change, because you mutated it in place, React thinks nothing happened, even if internal properties were changed. This leads to your UI not updating when you expect it to.
Okay, let's talk useEffect. This hook is arguably the most powerful in React, but also often the most misunderstood. It's the hook that allows your components to perform side effects. These are operations that interact with the world outside the pure React component tree. Things like fetching data from an API, setting up timers or intervals, manually manipulating the DOM, though that's less common now, or subscribing to external events or data sources.
Yeah, and a common mental model pitfall here is trying to view useEffect as a direct one-to-one replacement for the old class component lifecycle methods, like component did mount, component did update, component will unmount. That model is flawed and leads to confusion. The more accurate way to think about useEffect is as a mechanism to synchronize your component's state and props with some external system.
So how does it work? The useEffect hook takes two arguments, a setup function where your side effect logic goes, and an optional dependency array. If you leave out the dependency array completely, the effect function runs after every single render of the component, usually not what you want. If you provide an empty array, the effect runs only once after the initial render of the component, kind of like component did mount.
Right. And if you provide dependencies in that array, say count, userid, then the effect runs after the initial render, and it reruns whenever any of those specific values, count or userid in this case, change between renders. Now, omitting a dependency that your effect actually relies on is a very common and often serious error. It leads to something called stale closures, where your effect function closes over and uses an outdated value of a prop or state variable from a previous render. The slint plugin React Hook's exhaustive depths lint rule is specifically designed to catch this, and honestly, you should almost never ignore that lint rule unless you have a very, very good reason and understand the implications deeply. I've personally wasted hours debugging stale closure issues early on.
Good advice. And for effects that set up something that needs cleaning up later, like maybe a WebSocket subscription, or a timer using setInterval, you simply return a cleanup function from your useEffect setup function. React will automatically execute that cleanup function right before the component unmounts. And importantly, it also runs the cleanup before the effect runs again due to a dependency change. This prevents memory leaks and ensures effects don't pile up incorrectly. Okay, last building block in this segment. Handling user events. This is how your React apps actually respond to user input clicks, typing, form submissions, etc. The syntax is nicely declarative and integrated right into JSX. Event handler attributes are written in camel case, like onClick, onChange, onSubmit.
And a key thing to remember, you pass a function reference to the event handler attribute, not the result of calling the function. So onClick handle click is correct, onClick handle click is incorrect, because that would call the function immediately when the component renders, not when the click happens.
Right. And if you need to pass extra arguments to your event handler, like maybe an item's ID when clicking a delete button in a list, the standard way is to use an inline arrow function on click,
Right.
a delete rel ADE. You define a small function right there that calls your actual handler with the ID, and usually the event object E's.
Yeah.
Speaking of the event object E, the one passed to your handlers in React isn't the raw browser event, it's a synthetic event.
Yeah, it's a cross-browser wrapper provided by React. It gives you a consistent API for event properties and methods, regardless of which browser the user is on. Things like ePrevent default and eStopPropagation work reliably everywhere. It's a nice abstraction.
All right, we've got the core React concepts down. Now let's zoom out. Moving from building individual components to assembling a complete, deployable, production-grade application. This requires a shift in perspective, bringing in new tools and thinking about broader architectural patterns. First big piece, navigation. React itself doesn't actually have a built-in router. So for single-page applications, SPAs, where you want navigation without full-page reloads, the library React Routerdom is pretty much the de facto standard. It's what almost everyone uses for handling client-side routing.
Yep. And the core components you'll work with in React Routerdom are usually browser router, which you wrap around your whole app, usually at the root, then rates and read components to define mappings between URL paths and the components that should render for those paths. And crucially, the link component for creating navigation links. Using link to about instead of a standard HTML tag is vital because link prevents a full page reload. It just updates the URL in the browser bar and tells React Router to render the new component, enabling that smooth, fast SPA navigation feel. That's a key part of the modern web UX people expect. Oh, and there's also the use navigate hook. That's for when you need to trigger navigation programmatically, say, after a user successfully submits a form and you want to redirect them to a different page.
Okay, next big architectural decision. How do you handle styling? This is a surprisingly contentious topic sometimes. The blueprint highlights two dominant and philosophically quite different paradigms right now. CSS and JS libraries like styled components or emotion and utility-first CSS frameworks, with Tailwind CSS being the most prominent example.
That's right. Styled components, and CSS and JSS in general, lets you co-locate your CSS styles directly within your JavaScript component files, often using tagged template literals. This gives you truly encapsulated style scope to the component, and it makes it really easy to create dynamic styles based on the component's props. The styles live right next to the logic. Tailwind CSS, on the other hand, takes a totally different approach. It provides a huge set of low-level utility classes, things like Flex, Item Center, P4, BGBlue 500, and you apply these classes directly in your JSX markup, composing complex styles by combining many small utilities. The idea here is to prioritize rapid development and enforce consistency through a constrained design system defined by the utility classes.
So how do you choose between them? It really sounds like a clear trade-off. Styled components seems excellent if you need highly dynamic, prop-driven styling, and you value that strong component encapsulation where styles are tightly coupled to the component logic. Whereas Tailwind CSS looks fantastic for rapid prototyping, ensuring design system consistency across a potentially large team. Everyone uses the same utilities, and it provides great out-of-the-box responsive design utilities that are easy to apply.
Exactly. And there are performance considerations too. CSS in JS solutions like styled components can introduce a small runtime overhead because the CSS styles are often generated and injected into the document by JavaScript at runtime. Tailwind aims for near zero runtime overhead. The styles are mostly static CSS. However, to keep your final CSS bundle small in production, Tailwind relies on a build step using tools like PostCSS to purge or remove all the unused utility classes from your final style sheet. So there's a build time consideration there.
Okay, let's talk data fetching again, but at a more application-level pattern. Real-world apps are constantly fetching data, and a robust application needs to gracefully handle that entire lifecycle. Making the initial call, showing some kind of loading state to the user, handling potential errors gracefully, and then finally displaying the successful data.
Yeah, the foundational pattern for this usually involves managing 3 distinct pieces of state, typically using useState. One piece for the actual successful response data, one Boolean for the loading status, loading, and one for any potential errors, error. This state management logic is often encapsulated within a useEffect hook that runs, say, once on component mount, using as dependency. And inside that effect, you'll often use a library like Axios, which many prefer over the native fetch API because it offers conveniences like automatic JSON parsing and better error handling out of the box.
Right. And then the UI part uses conditional rendering based on that state. something like return loading spinner, if error message, and only if neither of those are true, you render the actual data, return my data, display data. It's a simple but very effective pattern for managing the UX around async operations.
Definitely. And a key best practice here, especially for promoting reusability and keeping your components clean, is to extract the entire data fetching logic, state management, the useEffect, the API, call into a custom hook. You might call it something like useFetch. This follows the don't repeat yourself DRY principle. It encapsulates all that complex asynchronous logic, and it significantly cleans up your actual UI component code. Your components then just consume the hook, like const data, loading error, useFetch paid users, and focus solely on rendering the UI based on those values. Much cleaner.
Okay, state management. As an application grows, managing state that needs to be shared across many different components becomes a really significant challenge. We talked about prop drilling earlier, just passing props down through many, many layers of components that don't actually need them just to get the data to a deeply nested child. That's a well-known anti-pattern. It makes code hard to refactor and understand. So choosing a strategy for managing this global or shared state is a critical architectural decision for any non-trivial React app.
Right. The question then becomes, what are the main options, and importantly, when should you choose each one? There's no single silver bullet. First, there's the React Context API. This is React's built-in solution specifically designed to avoid prop drilling. It's relatively simple to use and requires no external libraries, which is nice. However, its major drawback, especially concerning performance, is that any component consuming a specific context will re-render whenever any part of that context value changes, even if the specific piece of data that component cares about hasn't actually changed. So, context is generally best suited for low-frequency global data. Think things like the current theme, light-dark mode, or maybe the user's authentication status, stuff that doesn't change very often.
Okay, what else?
Next up may be something like Zustand. This has become a really popular modern choice. People often describe it as hitting a kind of sweet spot between the simplicity of context and the power of something like Redux. It has a very minimalist, hook-based API, so it's generally quite easy to learn. And it's highly performant because components can subscribe to specific slices of the global state. This means a component only re-renders when the specific data it actually cares about truly changes, not just when anything in the store updates. It's a great choice for many small to mid-sized applications where context might become too slow.
And the big one, Redux.
Right. Redux, especially when used with Redux Toolkit, which drastically reduces the old boilerplate, is the long-standing, battle-tested solution. It's often the choice for large-scale, complex, enterprise-level applications. Redux enforces a very strict unidirectional data flow. You have a single centralized store, you dispatch actions to describe changes, and pure functions called reducers calculate the new state based on those actions. This strictness makes the application's state highly predictable and much easier to debug, especially in complex scenarios. And Redux has an unmatched ecosystem, including incredibly powerful dev tools that allow for things like time travel debugging, stepping back and forth through state changes.
Wow, okay, so how do you, as an architect, navigate these choices? It sounds like there are significant trade-offs. You don't just pick the best one, right?
Exactly. There is no single best tool. An architect evaluates the specific project's needs. How complex is the state? What are the performance requirements? How large is the development team? Based on that evaluation, you select the most appropriate tool for that specific job. Choosing Redux for a small, simple blog might be massive overkill, introducing unnecessary complexity. But conversely, relying solely on the basic context API for a large, highly dynamic application with lots of shared state could easily lead to significant performance bottlenecks down the road. It's all about making informed, thoughtful trade-offs based on context.
Okay, perfect. Now let's really put on the architect's hat. We're shifting focus now from the how-to of building React apps to the deeper why behind architecting a robust system. An architect's primary concern isn't just making it work today. It's ensuring the application remains performant, scalable, and crucially, maintainable as it inevitably evolves over time. We're talking years down the line.
Yeah, and from a performance perspective, probably the most common source of degradation you'll encounter in React applications is unnecessary re-renders. Components rendering again when their output wouldn't actually change. It's something you'll constantly be looking out for and optimizing.
So what are the main tools in our toolkit to combat that? Memoization seems key.
Absolutely. Memoization is your friend here. React gives you a few specific tools. First, React.memo. This is a higher order component that you wrap around your functional component. It performs a shallow comparison of the component's props between renders. If the props haven't changed, React skips re-rendering that component entirely. Then there's useCallback. Now, this hook memoizes a function definition. This is important when you're passing callback functions down as props to child components that are themselves memoized using React.memo. UseCallback prevents the parent from creating a new function instance on every render, which would otherwise break the memoization of the child. And finally, useMemo. This hook memoizes the return value of an expensive calculation. It takes a function and a dependency array. The function is only re-executed and the value recalculated if one of the dependencies has changed. This is great for avoiding costly computations on every single render.
Okay, memoization helps with re-renders. What about initial load time? Big bundles can really slow things down.
Right, that's where code splitting comes in. This is another critical performance optimization technique. Instead of bundling your entire application's JavaScript into one single, potentially massive file that the user has to download up front, code splitting breaks the application down into smaller chunks. These chunks can then be loaded on demand, typically when the user navigates to a part of the application that needs that specific code. This dramatically improves initial page load times, especially for larger applications where users might only ever visit a fraction of the total features.
And React has built-in support for this, right?
It does. React provides React.lazy for dynamically importing components. You wrap your dynamic import call in React.lazy, and then you use the suspense component higher up in the tree. Suspense lets you specify some fallback UI, like a loading spinner, to show while the lazy loaded component's code chunk is being fetched over the network.
That sounds useful. What's a common strategy for applying code splitting?
A very common and effective strategy is route-based code splitting. You basically make each page or major section of your application its own lazy loaded component. So when the user navigates to profile, only then does the browser fetch the JavaScript chunk needed for the profile page.
Makes sense.
Yeah.
Any other performance tips for architects?
Well, if you're dealing with very long lists, maybe thousands or even tens of thousands of items, rendering all of them to the DOM at once will kill performance. In these cases, you need to look into virtualization, sometimes called windowing. Libraries like React Window or React Virtualized help with this. They work by only rendering the small subset of list items that are currently visible within the viewport, plus maybe a small buffer. As the user scrolls, they efficiently swap items in and out. This significantly improves rendering performance and memory usage for huge lists. And one last simple but crucial thing, always deploy the minified production build of React and your app code to your users. The development build includes many helpful warnings and debugging tools, but these add significant overhead and make the app much slower. You get this automatically when you run the npm run build with tools like Create React App.
Okay, shifting from code performance to project structure. This might seem less technical, but the way you organize your folders and files is actually a foundational architectural decision. It directly dictates how easily your application can scale, how easy it is for new developers to onboard, and how productive your teams can be as the codebase grows. It's not just aesthetics.
Totally agree. When you're starting out, a simple grouping by type structure might seem intuitive. Put all components in a components folder, all hooks and shooks, all utility functions and spittles and so on. And that works fine for small projects, but it really doesn't scale well for larger applications. Why? Because the files related to a single feature or domain of your application end up scattered across many different folders. This increases the cognitive load for developers. If you need to work on the user profile feature, you have to jump between components, hooks, styles, epi, maybe types. It gets messy fast.
So what's the recommended alternative for scalability?
The widely recommended best practice for scalable applications is a feature-based structure, sometimes called domain-based or module-based. In this approach, you co-locate all the files related to a single feature, the components, the hooks, the styles, the tests, maybe even API definitions within a single dedicated feature folder, like Stark Features Profile or Stark Features Authentication.
Ah, I see. So everything related to profile lives inside the profile folder.
Exactly. This promotes modularity. Features become more self-contained and easier to understand and maintain in isolation. It also makes it easier for different teams to work on different features concurrently without stepping on each other's toes as much. It really fosters team autonomy.
Does it have to be strictly one or the other? Grouping by type versus grouping by feature?
Not necessarily. Often, a truly robust, scalable structure ends up being a hybrid. You might have top-level folders for genuinely generic, reusable things like maybe a Circ components common folder for truly universal UI elements, buttons, inputs, or a circlib folder for core utilities. But then the bulk of your application code lives inside specific feature folders like Stark Features Products, Park Features Checkout, Circ Features Admin. This kind of structure often gives you the best of both worlds. Shared reusability where needed, but strong feature encapsulation for the main parts of your app.
Okay, let's talk anti-patterns. An anti-pattern is basically a common solution to a recurring problem that seems intuitive at first, but ultimately turns out to be ineffective or even detrimental in the long run. Recognizing these anti-patterns and knowing how to refactor away from them is the key responsibility for someone thinking like an architect, because they can silently erode maintainability, performance, and overall code quality over time if left unchecked.
Yeah, let's run through a few of the big ones you'll definitely encounter in the React world. Prop drilling. We mentioned this before. Passing props down through multiple layers of intermediate components that don't actually use the props themselves, just to get them to a deeply nested child that does. The solution usually involves rethinking your component composition, maybe using props not children, or reaching for context API or a global state management library if the data is truly global.
Right. What else?
Large components, sometimes called God components. These are components that try to do way too much. They violate the single responsibility principle. They fetch data, manage complex local state, handle user input, contain lots of conditional rendering logic, all in one massive file. They become incredibly hard to understand, test, and modify. The fix is decomposition. Break them down into smaller, more focused components, and extract reusable logic, especially stateful logic, into custom hooks.
Okay, what about lists?
Using index as key. This is a classic one when rendering lists of items using .map. Using the array index I as the key prop, like key I, seems easy, but it's dangerous. React uses the key prop to identify which items have changed, been added, or been removed between renders. If the list order changes or items are added or removed from the middle, using the index as the key can lead React to incorrectly match elements, potentially causing state inconsistencies, incorrect UI rendering, and really hard to debug glitches. The key must be a stable, unique identifier associated with the data item itself, like item.ad.
Crucial. And state mutation.
Direct state mutation. We hammered this home earlier, but it bears repeating because it's fundamental. You must never mutate state or props directly in React. Always use the state setter function returned by useState or the methods provided by useReducer or state libraries, and always provide a new object or array reference, typically created mutably using techniques like the spread syntax. Direct mutation breaks React's change detection mechanism.
And useEffect. You mentioned pitfalls there.
The useEffect minefield. Yeah. useEffect is powerful, but prone to errors if not used carefully. Common mistakes include missing dependencies in the dependency array, leading to those nasty stale closures we talked about. Creating infinite loops, usually when an effect updates a piece of state that is also listed in its dependency array, causing it to run again, update the state, run again. And forgetting to provide cleanup functions for effects that set up subscriptions or timers, leading to memory leaks, especially when components mount and unmount frequently. These are subtle but critical errors to watch out for and test against.
Okay, one more architectural concept, especially for really big applications. Micro-frontends. What's the idea there?
Right. For very large, incredibly complex applications, especially those being developed by multiple independent teams, think large enterprises, a micro-frontend architecture might be considered. It essentially extends the concept of back-end microservices to the front-end world.
How does that work in practice?
The core idea is to break down a monolithic front-end application, one giant code base, into smaller, fully independent applications. Each of these mini-apps might handle a specific feature or section of the overall UI. These independent micro-frontend apps are then composed together in the user's browser at runtime to create the final, unified user experience. Think of a page composed of independent widgets or sections, each potentially built and deployed by a different team.
What are the benefits of that approach? Sounds complex.
It is complex, but the potential benefits can be significant at scale. The main ones are team autonomy. Different teams can develop, test, and deploy their micro-frontends independently without needing to coordinate complex releases across the entire organization. Technology agnosticism, potentially. Different teams could theoretically choose different technologies. Maybe one uses React, another Vue, another Angular for their specific micro-frontend, though this adds significant integration challenges. More commonly, it allows teams to upgrade dependencies or adopt new versions of a framework independently. Improved scalability for development. It can make it easier to scale development efforts across very large organizations by breaking down the problem space.
But you mentioned challenges, so what does this mean for you if you're considering it?
It means you need to be aware of the significant trade-offs. Micro-frontends introduce substantial operational complexity. You need tooling and infrastructure to build, deploy, and compose these independent apps.
Okay.
There's a real risk of duplicating common dependencies like React itself, or shared component libraries across multiple micro-frontends, which can bloat the overall size of the application downloaded by the user. And you need very careful planning for things like consistent styling and inter-micro-frontend communication. How do these independent apps talk to each other? It's a major strategic decision. It's typically only justifiable for organizations with the scale, complexity, and engineering resources to manage the inherent overhead. It's definitely not something you'd reach for in a small or medium-sized project.
Right. Okay, so we've architected our app, we've written high-quality React code, but that's only one part of building a professional product, isn't it? The full lifecycle includes ensuring quality through rigorous testing, making sure the application is secure, and automating the deployment process so we can get our code to users reliably.
Absolutely. In any professional software development environment, testing isn't an optional extra or something you tack on at the end if you have time. It's integral to the process. Having a comprehensive suite of automated tests is what ensures stability, prevents regressions, bugs creeping back in, improves the long-term maintainability of the code, and, crucially, gives developers the confidence they need to refactor code and deploy new features quickly and frequently without breaking things.
The blueprint talks about the testing pyramid. Can you break that down?
Sure. The testing pyramid is a common way to visualize a healthy testing strategy. It has three main layers. Unit tests form the base. These should be the most numerous tests. They're fast to run, and they test the smallest units of your code, like individual functions or components in isolation, often mocking out dependencies. Integration tests are the middle layer. There are fewer of these than unit tests. They test how multiple units work together. For example, does submitting a form component correctly update a list component? Or does a component correctly interact with a mocked API service? End-to-end E2E tests are at the top. You should have the fewest of these because they are the slowest and often the most brittle to maintain. They simulate full user journeys through your application in a real browser environment, clicking buttons, filling forms, and asserting that the entire flow works as expected from the user's perspective.
Okay, and what tools do people typically use for testing React apps?
The standard go-to toolset these days is usually Jest as the test runner. It provides the framework for running tests, making assertions, mocking, etc., combined with React Testing Library, RTL. And RTL's core philosophy is really important here, and it's a bit different from older testing approaches. RTL encourages you to test behavior, not implementation details.
What does that mean in practice?
It means you should write your tests in a way that resembles how a real user would interact with your components. You avoid testing internal state or implementation details of the component. Instead, you render the component, you find elements on the screen using queries that are accessible to users like get by text, get by role, get by label text. You simulate user interactions with those elements using utilities like userEvent.click or userEvent.type, and then you make assertions about the resulting state of the UI that the user would actually see.
So the tests focus on the what the user sees and can do,
Right.
rather than the how the component achieves it internally.
Exactly. This leads to tests that are much more resilient to refactoring. If you change the internal implementation of a component, but its external behavior remains the same, your RTL test should still pass. This gives you more confidence to refactor and improve your code without constantly breaking tests, which saves a ton of time and frustration.
Makes a lot of sense. Okay, let's talk security. User authentication is critical for almost any real-world web application. The standard flow often involves the front end getting some kind of token, usually a JSON web token or GWT, from the back-end server after the user successfully logs in. Then, the front end needs to store this token somewhere and include it in subsequent requests to access protected API routes on the server.
Right. And this immediately raises a very important question, one with pretty profound security implications. Where exactly should you store that JWT on the client side? A very common practice you'll see, especially in older tutorials or code bases, is storing the JWT in local storage. But this is now widely considered a deeply flawed and insecure practice.
Why is local storage so bad for storing tokens?
Because local storage is directly accessible via JavaScript running on your page. This makes it highly susceptible to cross-site scripting, XSS attacks. If an attacker manages to inject malicious JavaScript code into your page, maybe through a vulnerable third-party script or user-generated content that wasn't properly sanitized, that script can simply read the JWT directly out of local storage and send it off to the attacker's server. Game over, the attacker has hijacked the user session.
Ouch. Okay, so if not local storage, what's the architecturally superior and more secure pattern?
The recommended approach is to have the backend server set the JWT, or preferably a session identifier linked to the JWT on the server, inside an HTTP-only cookie.
HTTP only. What does that flag do?
The HTTP-only flag tells the browser that this particular cookie should only be sent back to the server with HTTP requests. It makes the cookie completely inaccessible to any client-side JavaScript running on the page. Your React code literally cannot read it. The browser handles sending it automatically with every relevant request to your backend domain. This effectively mitigates the risk of token theft via XSS attacks, because even if malicious JavaScript runs on the page, it simply cannot access the cookie to steal it. It's a much more robust security posture.
That's a really crucial distinction.
Yeah.
What about protecting routes on the front end itself? Like preventing users from even seeing certain pages if they're not logged in?
Yeah, that's a common pattern too. You might create something like a protected route component in React that checks the user's authentication status, maybe by checking if the HTTP-only cookie exists, or by calling a me endpoint on the API and redirects them to the login page if they're not authenticated. But it's really important to understand that this front-end route protection is primarily a user experience UX pattern. It prevents unauthenticated users from seeing UI elements they shouldn't interact with, which is good. However, it is absolutely not a security guarantee. True security must always be enforced on the server side. Your backend API must validate the token or session and check permissions for every single request that accesses sensitive data or performs protected actions, regardless of what the front-end UI is doing. Never trust the client.
Got it. UX pattern, not security boundary.
Yeah.
Okay, final step in the professional lifecycle, actually getting our application out to users. Deployment. Typically, you run a command like npm run build or yarn build. What does that do?
That command triggers your build tool, like Webpack, Vite, etc., often configured via Create React App or a similar framework, to create a highly optimized, production-ready version of your application. It bundles your JavaScript, minifies the code, removes whitespace, shortens variable names, optimizes assets like images, generates static HTML files, and usually puts everything into a specific output folder, commonly named build or dist. This folder contains just static files, HTML, CSS, JS, images, that can be served by any web server.
And where do we put these static files? How do we host them?
Well, the options have gotten incredibly good and easy in recent years. Modern deployment platforms specifically designed for static sites and front-end frameworks like Vercel and Netlify have really revolutionized this space. They offer seamless integration directly with your Git repository, like GitHub. You put your code and they automatically build and deploy it. They also typically provide features like a global content delivery network, CDN, for fast loading worldwide, automatic HTTPS setup for security, custom domain support, and even automatic preview deployments for every pull request, letting you test changes in a real environment before merging. They handle a huge amount of the traditional operational complexity of hosting.
That sounds way easier than managing servers yourself. But what about the process leading up to deployment? You hear a lot about CI/CD.
Right. CI/CD stands for continuous integration and continuous deployment, or sometimes continuous delivery. It's the backbone of modern, agile software delivery. It's all about automating the entire process, from the moment a developer commits code to their Git repository, all the way through building, testing, and ultimately deploying that code to production or a staging environment. The goal is to make releases frequent, reliable, and low risk.
What does a typical CI/CD pipeline for a React app look like?
A common pipeline, often configured using tools built into platforms like GitHub Actions, GitLab CI, or Jenkins, would follow a series of automated steps, usually triggered on every commit to the main branch or when a pull request is created. 1. Trigger. The pipeline starts automatically on a Git event, like a push or merge. 2. Checkout code. It fetches the latest version of the codebase. 3. Install dependencies. It runs npm install or yarn install to get all the project's dependencies. 4. Lint and test. It runs linters, like ESLint, to check code style and potential errors, and then executes the automated test suite, unit tests, integration tests. Crucially, if any linters fail or tests fail, the pipeline stops immediately, preventing bad code from progressing further. 5. Build. If tests pass, it runs npm run build to create the optimized production build. 6. Deploy. Finally, it takes the static files from the build folder and deploys them to the hosting provider like Vercel, Netlify, AWS S3, etc.
So it's a fully automated quality gate and delivery mechanism.
Exactly. This automation ensures that every change goes through the same rigorous checks, catches errors early, and allows teams to ship high-quality code to users quickly and reliably, multiple times a day if needed. It builds confidence and speed into the entire development lifecycle.
Wow. Okay, we have covered a lot of ground today. We've really charted a comprehensive course, haven't we? All the way from the absolute foundational prerequisites of web development, HTML, CSS, JavaScript deep dives, right up to those high-level strategic decisions that truly define a production-grade React application. It feels like the journey from just being a developer using React to becoming someone with a real architect's mindset. It's
Yeah.
not just about mastering one specific tool or library, is it? It's more fundamental, a shift in perspective.
It really is. It's about understanding the why behind architectural choices. Why pick this pattern over that one? What are the long-term consequences going to be for performance, for maintainability, for the team? We saw how having that deep command of HTML semantics, CSS layout, and modern JavaScript isn't just prerequisite knowledge. It's the very language in which React's core concepts are expressed. Understanding the why of JavaScript's evolution, like with this and arrow functions, makes React's own patterns feel so much more logical, almost inevitable.
Yeah, and we internalize React's core principles too.
Yeah.
That declarative nature enabled by the virtual DOMs optimization, the power and expressiveness of JSX when you understand it's just JavaScript transformation, and the fundamental modularity you get from thinking in components. And then we explore the building blocks, props, state effects, understanding the nuances, that strict one-way data flow, the absolute necessity of immutability for predictable state updates, and how useEffect is really about synchronizing your component with external systems, not just mimicking old lifecycle methods.
And when we zoomed out to the application level, the decisions became explicitly architectural, didn't they? Choosing your routing solution, your styling methodology, your global state management library. These aren't just technical implementation details, they are significant architectural decisions involving clear trade-offs. An architect doesn't waste time searching for a mythical single best tool for everything. Instead, they critically evaluate the specific project's needs, its scale, its complexity, its performance requirements, the team's structure and experience, and then select the most appropriate tool for that specific job. It's about context and informed choices.
And finally, we saw how the architect's lens has to extend beyond just the code itself. It encompasses the entire professional ecosystem surrounding the application. It's about actively championing a culture of quality through rigorous automated testing. It's about advocating for security-first patterns, like understanding why HTTP-only cookies are superior to local storage for session management. It's about designing scalable project structures that help teams work effectively. And it's about building those automated CI/CD pipelines that reliably transform lines of code into robust products that users can actually depend on.
And the journey definitely doesn't end here, does it? The React ecosystem is famous, maybe infamous, for being in a constant state of evolution. New patterns emerge, new tools gain popularity, even core features within React itself, like the recent introduction of server components, are constantly reshaping the landscape and how we approach building applications. So, what does all this mean for you listening now? I think the true mark of an architect in React or any technology isn't necessarily knowing every single answer off the top of your head. That's impossible. It's about possessing the solid foundational knowledge and the core mental models needed to ask the right questions, to evaluate new technologies critically, understanding their trade-offs, and ultimately to guide teams in building applications that are not just functional today, but are also robust, scalable, secure, and hopefully a delight to use and maintain for years to come.